Okay, so we've been talking a lot about superconductivity, where it comes from, the origin of the superconductivity, and this type of plot that you see over here shows you how much research has actually been poured into something so peculiar. And from the beginning of this timeline, where we see all of the type of material that we recognize, which are all metallic, intermetallic, alloys, and stuff like that, if you see the different markers kind of tell you the different materials that have been explored for superconductivity business. Now, down to this point, where there were all the Nobel Prize in Physics and physics exploration, the main point was that superconductivity was a sort of curiosity for the physicists, because he had a lot of insight on solid state physics, so physics of the condensed matter, but it's a kind of crossover in which you touch from the physics into the chemistry very easily. And one of the biggest breakthrough that have been into this field was in 1986, in which they touched onto something that are the high temperature superconductors. And this was the first big leap of this thing, was discovering this oxide phase, which, unlike the intermetallics, is a bit more like the complex oxides that we've seen in batteries. And to begin with, in this composition, it was a lanthanum, strontium, copper oxide type of phase. We showed the superconductivity at 36 Kelvin, and this was already a Nobel Prize in itself. But the big leap here was the synthesis of what is known as yttrium-barium copper oxide that had superconductivity at 91 Kelvin. So this is a real high temperature superconductor, because 91 Kelvin means that the superconductivity of this phase is achieved at liquid nitrogen temperature, not liquid helium temperature. And there are a series of modifications of these cuprates that can actually be achieved with retaining superconductivity in liquid helium temperature. So the very first one of this family has still low temperature superconductivity, which was supposed to be the standard. And then the high temperature superconductivity was the big breakthrough. So this was the moment when a lot of solid state people started to realize that modifying the material could achieve something that could go from a general super low temperature behavior to a behavior that you could actually push to higher temperature. That said, you can notice that there has been a bit of a lag in the field. There has been nothing so far that actually reaches the very elusive point of room temperature superconductivity, which will be the dream. But so far, nothing has really cut that edge. It's very difficult to reach, and the field has been trying and failing and trying and failing to make something that actually breaks that limit. A lot of the very higher temperature superconductors are superconductors at incredibly high pressure. That doesn't mean that there aren't a lot of chemists in combination to condensed matter physics that are actually working on these things. There are several groups and several people that work on it. And you can also see that there are some molecular materials that actually they also have this behavior, but you're going to discuss it in more length in the tutorials. Now, with room temperature, like high temperature superconductivity, like the yttrium-barium copper oxide material, we have a slightly different behavior from the basic metallic behaviors that we've seen before, because these are known as type 2 superconductors. There are some metals that are superconductors and are like standard superconductors that have a type 2 superconductivity, but all high temperature superconductors behave in this way. So in the type 1 that we saw before, This phase diagram was kind of straightforward, two different regions depending on temperature and field. You're either a normal state or you fall down into the perfect diamagnetic superconductive state, limited by a single critical field and a single critical temperature. In a type 2 superconductor, you kind of have more parameter and more possible regions of action of your material. So first thing is this this very low region of superconductive state, which is what we call the Meissner state, and in this state is achieved below the critical temperature and below a first critical field. So this is the lowest thing that you can find when you are below the temperature and basically when you're not applying a field or when you're applying a very low field. Here you have the same business that you see in a type 1 superconductor. You have a perfect diamagnetism, your material pushes out the field, and that's it. Then you have a second region that is still a superconductive state, still below the single critical temperature of the material. So the material only has a critical temperature, but it will show you two critical fields. So if you start applying field to your material, you don't immediately switch back to the normal state. You can retain the general superconductive state, but in the region between the first and the second critical field, your material behaves like a vortex superconductor. So this means that there are, instead of having no penetration of the field inside, there are some line of field of this external magnetic field that you apply to your material that are able to pass through your material, but only in super narrow regions. So instead of having this thing as the normal state, for which if you apply an external magnetic field, you expect it to pass through the material, here it doesn't pass through the material unless it's in the vortex point. So the key requirement here to be able to actually apply these superconductors in like when they are in a vortex state is that you can actually pin the vortex, because what you don't want is that the vortex can actually move through the surface of the superconductor. You want to make sure that as it passes through, it will pass through in only very specific regions that you can actually control. And in case, like, basically this thing is called the vortex pinning, so you make sure to pin it down in a certain position. It can be done with crystal defects, some homogeneities in the sample, impurities, so these points become the point in which the vortex can actually pass through. When the vortex are unpinned, and you have several of them, it can happen that they will spontaneously arrange themselves in a way that optimizes the repulsion, because a vortex doesn't like the other vortex. So as you are passing through a series of magnetic line of field, you find yourself with multiple vortexes, and these vortices will arrange themselves in like hexagonal shape or stuff like that. It's particularly like mesmerizing to look at. And if the vortex are pinned, but they still form in a very random way, then you can call them like a vortex glass. So you see this passage of vortices, and it's still a very peculiar state. So the big question here is, do you have Cooper pairs when you have this business? Because we've been discussing of like how the BCS theory of superconductivity explains how you have a superconductor. You have a superconductor because you create Cooper pairs below the critical field and below the critical temperature. Do you have the same here? This is a difficult question, because the BCS theory is proved and thermodynamically and quantum mechanically sustainable only up to a point of like 40 Kelvin. When you throw something like a high temperature superconductor that is superconductive at 100 Kelvin, this is way over the border of the BCS theory holding up. At this point, you will have to have correlation lengths that are way too high for your phonon-electron Cooper pair coupling for the Cooper pair to actually form. So the theory will not hold, the quantum mechanics will not hold, it wouldn't make sense, but still your material is superconductive. So this is the definition of a very hot debate. So every time someone tries to explain what is superconductivity and why is superconductivity at high temperature, if you throw the ball into a conference of solid state people, there will be a fist fight. So this is a comment that is going around and people are trying to reproduce the same feat that they did with the BCS theory, but is proven elusive. Like there is always some pitfall of some kind of interaction that doesn't quite hold if you try to do it in the way you were expecting. The fact that you have superconductors that can actually become superconducting at the temperature of liquid nitrogen means that we can find ourselves with incredibly nice video, because I can show you what the Meissner state looks like on a material that is a high temperature superconductor, because it means that instead of having it in liquid helium, which is impossible to actually keep around if you don't have it in a GUR, because it will just immediately evaporate off, you can actually look at a superconductor entering the superconductive state. So in this very nice video of this guy showing us the Meissner effect, is actually using three different things. The yttrium barium copper oxide, so this is high temperature superconductor, it's a pellet, you put the pellet down, that's a cube of a magnet in normal state. So this is hot, you can see nothing happens. But then he has a bottle of liquid nitrogen, and you can pour down the liquid nitrogen directly on the material, and this can happen because it's liquid nitrogen, you can manipulate it. Now you can see that the first part that you drop, it's a huge boiling point, because the liquid nitrogen needs to cool everything down. You want to bring all of your material at liquid nitrogen temperature. Everything that is keeping it hot is making it evaporate. So, but you can see that as it cools down the surrounding, the boiling of the liquid gradually decreases and the material slowly stabilizes. And now that it's actually at liquid nitrogen temperature, you can see that your magnet is suddenly floating on top of your superconductor. So this is the Meissner state. So this is sort of done in the reverse fashion. So you are floating a magnet on top of a superconductor rather than doing it the other way around. But this still works, because basically this means that the line of field that your magnet is trying to impose are being repulsed when it tries to touch the superconductor. And so this thing floats. And you can spin it, you can try to move it, but you can see that it floats in a very specific position, because this is giving the line of field and everything is being pinned out. So it's a very, very pretty thing to look at. You can notice, of course, since this is cooled in liquid nitrogen, but the liquid nitrogen is slowly evaporating, that this material is warming up very slowly. It's still in superconductive state. You can see how easy it is, how frictionless it is to actually spin something when in superconducting Meissner suspension. But you will notice that as the liquid nitrogen slowly evaporates, the material is actually starting to warm up. When it warms up, you lose the Meissner state. When you lose it, your metal drops. And that's our business. Now the big question is how does it work? What is yttrium barium copper oxide? So the yttrium barium copper oxide in itself, superficially speaking, when you just look at the arrangement of the cations in this material, looks like a perovskite that you've seen in previous tutorials, but with a stacking that is a bit different. So you have like a cube of copper. You stack 3 perovskite units, but one of them has barium, the other one is yttrium, the other one is barium inside. So you stack them along the C direction. So 2 of these are with barium, and the other one has indium inside. Superficially, this looks like an easy structure. But the thing that is missing here is, where is the oxygen? The oxygen here is a very big trick, because you have a deficiency in oxygen. So whereas normally in a perovskite, all these sites will be octahedral. So all of the copper sites will actually be perfect octahedral, because that's what a perovskite is. Here you have an oxygen deficiency. So when you try to build up your octahedra, you actually find yourself with a series of non-stoichiometry of oxygen. So in the 2 up thing, you kind of have a stoichiometry of barium, copper, oxygen 2.5. So basically the barium has like some deficiency in the coordination, the copper as well as some deficiency in the coordination. The middle unit instead has a stoichiometry of yttrium copper oxide O2. So it's missing 4 oxygen to have the full coordination. So this thing should be fully octahedral, and instead you will find yourself with something that looks more like a square pyramid or a square planar arrangement. So you can either find yourself with square pyramid units on the xy plane. So if this is C, this is x, this is y. So you have the planes of the pyramid in the xy plane. And instead you have square planar units parallel to the y. These units are linked by the corners, as are these units, but these are the corners of the planes, and these ones are the corners of just the corner of a square planar coordination. Now, the beauty of this thing and the chemical and solid state chemistry complexity is that this enforces the fact that you must have different oxidation states of the copper as it's going around. So whereas superficially you might look at this and be like, oh, this is copper, this is barium, this is yttrium, knowing that the coordination is different is something that is allowed to you by the solid state, because you can change the oxidation state of the same atom in a solid state arrangement and have a different thing. So you find yourself with this thing over here, which is copper O4 sheets, square planar coordination, and this thing instead is copper O5 with square pyramid coordination. So already pretty to look at, but what this is telling us is that as a chemist you sort of know what is the preferential coordination depending on the oxidation state, because you want to optimize the way the orbitals are actually chaining with each other. So having this sheet of square planar coordination is telling us that your copper should be in D8 type of oxidation state. So your copper is a 3D atom. You will have 5 different d orbitals. The best arrangement of the d orbitals to have a square planar coordination is this one, and the most stable oxidation state that you must have is the D8, because it fills up everything and it leaves one completely free up. So this means that this thing should be roughly an iron 3+. plus. Whereas when you want to put a square pyramidal coordination, this is basically same business, but it's stabilized by nature of having an additional electron. So this should be a 3D9 type of configuration, so it should go towards a copper 2. So these are effects of the distortion of the crystal field, basically. So when you use the crystal field to look at what your atoms can actually do, and you put it in a solid state, you can find yourself with the same atom, different coordinations, in a crystal arrangement. That means that you have a mixture of states. So this is already interesting in itself, and this creates infinite sheets of iron 3 plus, and infinite layers, because you have these XY layers of iron 2 plus like material. Now this means that the oxidation state in yttrium, barium, copper oxide, if you assume that you still have yttrium, barium and oxygen in the usual oxidation state, so 3, 2, minus 2, even though there are some wondering about is this oxygen actually a bit weird, so you have oxide ions in oxygen minus instead of oxygen 2 minus. That's an additional argument. But if you assume the 3, 2, minus 2 arrangement of yttrium, barium and oxygen, then this leaves you with a mixed valency on the copper, which is something that we already seen in batteries and stuff like that, because if you can change the oxidation state, it means that statistically speaking, throughout your structure, you should have an average of 2.33, something like that. But the alternative view of this thing is that basically you regard the base of the pyramid as a copper O2 infinite sheets type of stoichiometry, and you have this partial oxidized. But now this kind of begs the question of what is going on in the bands, because you will have the copper and the oxygen with their 3D and 2p orbitals. If they overlap with this partial oxidation, you will have a metallic state, right? And this is actually something that you see, so we can prove it, because you have a metallic normal state. So when the material is not superconductive at room temperature, if you make a crystal of yttrium, barium, copper oxide, you have delocalized electrons in the XY plane. This means that if you connect your measurement of conductivity on the crystal anisotropically, so if you connect it on the Z direction or the C direction, you don't see a big conductivity, but the conductivity is much higher in the XY plane than it is when you go over there. So it's a 2D layered conductivity, even though the structure is 3D. So basically with this thing, you know that the oxidation state is your trick of giving electrons to bring around, and the more oxidized part has this copper oxygen bands that actually give the conductivity, and you can have a charge transfer, so this electron can actually jump in the pyramids and possibly out of the pyramids into the square planar unit. So it kind of looks like a positive hole thing, because you have this empty possible orbital in which you can actually make the thing jump around, but it primarily involves this thing. So as we wonder, that we know that trying to make Cooper pairs here, it's a mess, but in this description you could basically have a superconductive state that depends also on this presence of the positive hole. So you can use the layers here of your square pyramid coordination as the charge reservoir, because that's the oxidation state that will kind of hold the additional electron. And the one that is nominally 3 plus is your electron sink, so where the electrons can actually go. And there is an internal transfer of charge that can actually make your material work. So the electrons are supplied by this square pyramid thing that has oxidation state copper 2 plus like, and the sheets over here that have an oxidation state copper 3 plus like are the one that can actually be oxidized if you manage to bring the electrons around. Now, with the fact that this thing is incredibly susceptible to oxidation states, you have this thing that is very susceptible to reduction, so copper 3 all over the place, and this thing that should be mostly unaffected by reduction. But given that you want to be able to tweak the oxidation states of this, and if the oxidation state is not what you expect and not averaged in the way you expect, your material might very well not behave in the way you think. The superconductivity in this material is incredibly dependent on this. So it is the oxygen deficiency that is giving you the power to change the oxidation state of copper. So if you tweak and you kill your oxygen content, so this oxygen deficiency is the thing that is giving you the capability of having these electrons going around. And we know that if you don't synthesize your material properly, so this oxygen deficiency is not properly put into place, you might completely lose the superconductivity, because the superconductivity is coming from the charge average. So the oxygen content, depending on how you try to control it upon synthesis, could lead you to plateau of very specific temperature of transition of superconductivity, or you can get a smooth line of where do we block. If you don't make it properly and this thing is maybe completely oxidized, your material is simply not superconductive, which can happen, but is not what you want to happen. Now, very quickly, we are going to go through some concepts of applications of superconductivity, but you'll have time to explore it explore it more as well in the tutorials. One of the things that you need to consider is that the biggest business of a superconductor is that a superconductor can conduct electricity without resistance. This means that you have no losses, and if you put a current through a superconductor, as long as the superconductor stays in superconductive state, then you actually keep your thing going indefinitely. So you could pump up the current without having to worry about the losses. Now, this thing also means that if you can spin a huge amount of current through a wire, you can also make an incredible amount of magnetic field. So usually in applications, you still tend to use the low temperature superconductor. You don't use the high temperature superconductor. And you need to remember here that when you want to pump up this current, there is actually an additional thing that is sort of correlated to the fact that you have a critical field. You want your current to be below a certain critical value. So you could push your material out of superconductive state just because you're pushing your current too high. Superconducting magnets, so these are electromagnets, these are magnetic things that you create by electricity, can actually go very, very up, but you need to be able to win them properly. So this is the mechanical trick, and you need to have a fail-safe in case you lose your superconductivity and your thing completely falls off the business. So you need to increase this thing slowly and have a fail-safe. Another thing that is actually something that you might have seen but never actually thought about, oh, this is how it works, is the superconducting magnetic levitation, so the maglev trains that you have mostly in Japan. And they go to incredible speed because in this case you don't have the friction to block your maglev train. So you are using superconducting magnets to create these huge magnetic fields. And by nature of having magnets of different orientations, the train is completely automatic. So depending on how you orient the magnet, you can make your train speed up to incredible speed, which can go to 600 kilometers per hour, but you can also make it brake and stop without having to use any additional thing. So this thing is completely automated, and it's automated by tweaking the tracks. Once again, this is using low temperature superconductors. You don't use high temperature superconductors, but if you can have a closed environment in which this thing is kept at liquid helium temperature, this will actually work regardless. And you can see here a schematic of where do you put the magnets on the tracks and on the material. So you can actually make it interact, and as it interacts, it sort of like lifts up. One of the most interesting applications of superconductors is actually something that I told you was a spoiler last week, because last week we were wondering how do you actually measure magnetism in a material. So to measure magnetism in a material, you need something that is incredibly sensitive to make sure that you can actually measure those susceptibility curve, measure the hysteresis. So you don't only need a possible generation of field, you need something that will measure the magnetic response. So what you have in this business is actually something that uses the Josephson effect of the supercurrent. So a Josephson-Johnson functions on the basis that you have a junction between a superconductor, and your Cooper pair is going through a tunneling type of effect. So if this is a superconductor, this is a superconductor, this is an insulator, to pass from one side to another, you have a tunneling. So you can only go from one to another if your material is actually jumping through the junction. So you have two superconductors and a weak link behind. The link is insulating, and you basically have the physical constraint of you need to pass through here. So this is a macroscopic quantum phenomenon, because this is quantum tunneling, but the junction is actually a material. So the tunneling of Cooper pairs electron through the junction gives you this Josephson effect. So that when a DC current is applied, you have a response of the material, right? So you see you have an oscillation of frequency at the junction, because regardless of the equilibrium that you have, the current is proportional to the phase difference of these two things at the side. So this thing gives you a very standard, super low, super precise, fundamental measure of voltage. So the voltage that you can measure with this thing is at 1 part to the 10 to the 10. So any modification of voltage that you impose on the junction can be measured and will be measured, because the junction is incredibly sensitive. So why is this interesting for us when we actually have when we want to measure magnetic effects? Because we have this biasing current passing through, but when you have your material in a SQUID, so superconducting quantum interference device, you have your junction, and your junction is at interaction distance with this sort of like normal coil. So if your material is passing through the coil and your material is magnetic, it means that this thing can, like this voltage that you measure, can be converted in a quantized magnetic flux thing. because again, voltage that you measure could come from like any difference in the voltage that you measure could come from a Lorentz effect of the passage of a magnetic material into something. And this thing is incredibly precise because any small variation will be detected by the power of the Josephson junction. So this thing is low enough that you can measure the brain waves of living organisms. So it's a very low magnetism. Like the magnetism of your brain, it's there, but it's low. The squid has enough power to actually measure it. So you can change, like any change in magnetization up to 10 to the minus 14 Tesla can be measured. This means that when you have your material, you're cooling it through. That's fine. So you cool and your material goes through a magnetic transition. The squid will tell you, oh, I'm measuring a difference in current. This is the signal of your material. So you can get those susceptibility curves as a conversion of the signal that the Josephson junction is measuring. Now, this concludes our part on superconductor. The next thing that we're going to have is going to be completely different, and is going to be on lasers material.